Alright, this is our video on calculating delta H, or calculating enthalpy, using Hess's law. Okay, and so the first thing we're going to do is we're going to remind ourselves what Hess's law says. Hess's law tells us that the total enthalpy, and remember enthalpy is the heat of the reaction, or delta H, the total enthalpy for a reaction is the sum, or the addition of all of the changes within the reaction. And so we're going to learn how to manipulate partial reactions in order to get a net reaction. These partial reactions would come from a table that would be found like in a textbook for known changes in enthalpy for reactions, and if we add all of those changes together, we'd be able to get the total enthalpy change for the reaction. So we're going to have to manipulate reactions. Manipulate means to handle or work around. And so there's three kind of things we have to remember when we're manipulating reactions. If we have to, say, double the reaction, or half the reaction, or times it by 3, anything that we have to do to the reaction, whatever we do to the reaction, we have to do the same thing to the enthalpy, or the delta H, for that part. And you'll see what I mean about that in just a second. The other thing is that if we have to reverse the reaction, if you have to flip the reactants and the products, then you're also going to reverse the sign. So if it was a positive delta H, it would then be a negative delta H, and vice versa. And finally, sometimes we have to watch out for the states of matter, because sometimes they actually do matter whenever we're canceling out to get our net reaction. So let me kind of just show you what I'm talking about when I'm saying manipulating reactions. Let's say that our reaction given to us in a data table is N2 plus O2 yields 2NO. And for that reaction, the delta H is negative 180.5 kilojoules of energy. Well, let's say that I needed to reverse that reaction, so I needed to have the 2NO as a reactant. If I flipped like that reaction like I have here in the blue, then I also had to flip the sign. So I went from a negative 180.5 to a positive 180.5, and that's because I reversed the reaction. Or let's say, in comparing the first reaction to the second reaction, let's say I needed to double this, so I needed it to say 2, 2, and 4. Well, if I was going to double it, 2, 2, and 4, I also would have to double the 180.5. So 180.5 times 2 would be the negative 361 kilojoules. So remember, if you are going to double it, half it, times it by 3, whatever, you have to do the same thing to the delta H. And if you're going to reverse the reaction, you're going to have to reverse the sign. And as long as we take care of that, it should be pretty easy. Okay, so what I need you to do now is I need you to get your worksheet, and these are our practice problems on page 18. Interactive Notebook, page 18, Hess Law worksheet. We're going to be looking at 2, 4, and 5. We did number 1 together in class, and number 3 is not the type of problem that we're looking at for this worksheet. So just 2, 4, and 5. And we're going to start with number 2. Calculate the delta H for the reaction 4NH3 as a gas plus 5O2 as a gas, yielding 4NO in the gas state plus 6H2O in the gas state. And you can see how we have these partial reactions that we're going to manipulate in order to get to add up to an overall reaction. Okay, so here we go. The first thing that I do when I see one of these problems is I go ahead and I label my reactants and my products, and I'm just going to color code these. So I see NH3 in the gas state is going to be a reactant, and O2 in the gas state is going to be a reactant. So now I'm going to go in and look at my data that's given to me, and I'm going to try to find any instance of NH3 in the gas state. So none there, none there. Oh, but here's NH3 in the gas state. And is there any NH3 here? Nope. All right, so let me go back and look for O2 in the gas state. Well, I see O2 in the gas state here, and I see O2 in the gas state there. Okay, now I'm going to go back in and I'm going to find my products. So I'm going to look for NO in the gas state, and I see it here. And then I'm going to look for, it's not here and it's not here, I'm going to look for H2O in the gas state. Well, I see H2O in the gas state here. Okay, so these are the items that I've marked in blue are the ones that I'm going to be looking for. The ones that were not marked are going to be ones that cancel out in our reaction. And the way that they're going to cancel out in the reaction is that they're going to show up on both the reactant side and the product side. And so when we add our reactions together, they're going to cancel out. Okay, so let's start by writing our reaction. Okay, so I need NH3 to be a reactant. So I'm going to start with NH3. Well, I found NH3, but there's a couple of problems with it. The first thing is that I need there to be 4 NH3s, and there's only 2 NH3s. So I know that in order to get from 2 to 4, and there's no other NH3 in my problem, I'm going to have to double it. So I'm also going to have to reverse it. Right now NH3 is in the product side and I need it to be in the reactant side. So I'm going to have to reverse my reaction. Well, I know if I reverse my reaction, I'm going to reverse the sign. So this was a negative 91.8, but now it's going to become a positive 91.8. I also know that I'm going to have to go from a 2 to a 4, so I'm going to have to multiply this by 2, which means I must also multiply this by 2. So I'm going to go ahead and write that down as the reverse. So if I multiply it by 2 and I reverse it, it would be 4 NH3 as a gas yields, now it's going to be 2 N2 as a gas plus 2 times 3, 6 H2 as a gas. Okay, and I know that my delta H for this is now going to be 91.8 times 2, and it's a positive sign now, so 183.6, positive 183.6. Okay, so I've dealt with this reaction. Now I need to look at my other reactions. Okay, so I've dealt with NH3. Now I have my O2s, and I see that I've got O2 here and O2 here. That kind of makes it weird, so I'm not going to worry about the O2. I'm actually going to skip to the NO as my next. So let me find my NOs. I have an NO here and nowhere else. So that makes it kind of easy. Well, I see that I have 2 NOs, but I need it to be 4 NOs. The good thing is that NO is written as a reactant, a product here and a product here. So they're on the same side of the sign, so that's going to be a good thing. Okay, so I'm going to put my reaction in, but I know that I'm going to have to, again, double it, so I'm going to have to double my enthalpy. So when I write this down, it's going to be 2N2 plus 2O2 yields 4NO, and my delta H is now going to be negative 361 kilojoules, and that's because I multiplied it by 2 because I had to double my reaction. Okay, my last reactant here is going to be H2O. Well, I need 6 H2Os. Well, I see that there's no H2Os except for this problem. So in order to get from a 2 to a 6, I'm going to have to multiply by 3. So I'm going to have to multiply this by 3. So I'm going to write my reaction in. They're on the same side from what they need to be. So when I write my reaction in, it's now going to be 6 H2 plus 3 O2 yields 6 H2O, and my delta H for this reaction is going to be negative 483.6 times 3. And so I get negative 1450.8, negative 1450.8 kilojoules. Okay. So let me just go back in really quickly and make sure that I have all my signs written in. This was a gas. N2 was a gas. This was a gas. This was a gas. Oh, everything's in the gas state. Okay, well, since everything is in the gas state, that makes it easy because I know that they're going to cancel out. So now I'm just going to go in and I'm going to see what occurs on both the left and the right hand side of the arrow. And sometimes what I do is I go in and I circle the things that are going to end up in my equation first. So like NH3 is going to end up in my equation, my O2s are going to end up in the equation, NO is going to end up in the equation, and 6 H2Os are going to end up in the equation. So I need to see if anything else will cancel out. Well, I see that the N2 and the N2 will cancel out, and I also see that the 6 H2s and the 6 H2s will cancel out. If I wanted to, I could write this as one formula, and it might kind of help you to understand how we're doing this. So I'm going to go ahead and write everything that's on the reactant side, and then everything that's on the product side on the product side. So 4NH3 plus 2N2 plus 2O2 plus 6H2 plus 3O2. And you can see how that's all what was on here on the reactant side. Yields, and I'm going to write everything that was on the product side. 2N2 plus 6H2 plus 4NO plus 6H2O. And so basically that's what adding all these reactions would be. And then I'm just going to go in and see what can I group together and what can I cancel out. So I have 4NH3. It doesn't occur anywhere else, so 4NH3. I have 2N2 and 2N2. This is on this side and this side of the equation, so they are gone. 2O2 and 3O2 on the same side of the arrow, not occurring anywhere else. makes 5 O2. And I have 6 H2 at 6 H2. Will those both occur? So cross them out. And then the only thing I have left is 4 NO plus 6 H2O. So we can see that now my final reaction is the same thing as the reaction I was initially wanting for my problem. So all I have to do now is just add up the enthalpies. So I have 183.6 plus negative 361 plus negative 1450.8, and the answer that I get is that my delta H is negative 1628.2, and since delta H is negative, I know that this was an exothermic reaction. And so this is actually my final answer. It's just my delta H. Again, so I manipulated the equations, I added them all together, and then I added up their delta H's once they had also been manipulated to get my final answer. Okay, so that's calculating the delta H for a net reaction. I'm going to go in and I'm going to show you two others kind of quickly. Okay, so my next problem says calculate the delta H for the reaction for CH4. Now remember that we are skipping number 3 and we are moving to number 4. Now here's the thing that kind of gets interesting. In class, before when we balanced equations, they've always had to be whole reactions. That isn't necessarily the case when we're using Hess's law. We can actually take half of a reaction if we need to. So we're going to go in, we're going to use our same strategy. We're going to highlight things that are on the reactant side, and then we'll go in and highlight the product side. So CH4. Anywhere I see CH4, okay. And NH3 in the gas state. Here's NH3 in the gas state, and that's it. All right. HCN in the gas state is now a product. That's here, and then H2 in the gas state. There's some H2 here, here, and here. Okay, so I just pick one and kind of go with it. CH4, CH4. Okay, so all I'm going to have to do is come in and write this reaction, but I do notice that I have CH4 as a reactant, and this is CH4 as a product. Since I have it since I need it as a reactant, I'm going to have to reverse this reaction, which means that this is going to have to become a positive 74.9. So I'm going to go ahead and reverse this reaction so that it'll be CH4 in the gas state becomes C in the solid state plus 2H2 in the gas state, and my delta H for that will now be positive 74.9 kilojoules. Okay, dealt with that reaction. Now let's do NH3. Okay, well NH3 is here. NH3 again is in the product side, but I need it in the reactant side, so I know that I'm going to have to reverse my reaction. But I also notice that I have 2 and I only need 1. Well, how can I get from 2 down to 1? I'll have to take half of the reaction. So that means I'm going to have to take half of the delta H. Okay, so I've had to take half of the delta H. So now when I write this in, I'm going to have to reverse the reaction and then write half of each of these. So I'm going to start here with NH3, but instead of writing 2, I'm going to write half of 2, which is going to be 1 NH3. So I have NH3 in the gas state becomes, and so now I'm going to have 1/2 N2 in the gas state plus 3/2, which is 1 1/2, right? 3 over 2. 3 divided by 2 is the same thing as 1.5 or 1 1/2, so I'm going to write that as 1 1/2 H2s in the gas state. And I know that my delta H now is going to be positive, but it's going to be half of 91.8. So 91.8 divided by 2 is 45.9. So 45.9 kilojoules. Okay, so now I've dealt with this reaction, so I have my final reaction that I need to deal with. All right, so in my final reaction, I am dealing with my HCN. Okay, so HCN is on the correct side. It's a product here and a product here, but again, I see I have 2 HCNs and 1 HCN, so that means I'm going to have to take half of this reaction, so half of its delta H. Okay, so let me write this in as half. It's going to be 1/2 H2 plus 1C plus 1/2 N2 yields 1 HCN, and these are gas, solid, gas, and my delta H is going to be half of this, so 270.3 divided by 2 is 270.3 divided by 2 is 135.15, so positive 135.15 kilojoules. Okay, so I'm going to go in and write my reaction as one whole reaction, and then I'll go in and see what I can add together or cancel out. Okay, so I'm going to have CH4 plus NH3, that's as a gas and as a gas, plus 1/2 H2 as a gas, plus 1 C, so C as a solid, plus 1/2 N2 as a gas, yields, and now on my other side, C as a solid, plus 2 H2 as a gas, plus 1/2 N2, plus 1 and 1/2 H2, and I ran out of room, plus HCN. Okay, so let's go in and see what I can group together and what I can get rid of. So I have CH4. I don't see CH4 anywhere else in my equation, so CH4 plus, so I'm done with that one. NH3. I don't see any more NH3 in my equation, so NH3 plus 1/2 H. Well, let's see here. I have 1.5 H's, so 1/2 H2 would cancel out the half there. Okay, so I don't have to deal with that one. I have carbon here as a reactant and carbon here as a product, so I can get rid of both carbons. And I have 1/2 of a nitrogen here and 1/2 of a nitrogen as a product, so I can get rid of my nitrogens. So I just have yields. And let's see here, I have 2 H2 and 1 more H2. Well, 2 H2s plus 1 more H2 is 3 H2 plus, so I'm done with those, and then an HCN. HCN. Alright, so let's double check and see. I have CH4 and CH4, NH3 and NH3 as reactants. I have 3 H2s as a product and 1 HCN as a product. Okay, so I got my reaction, which means that all of these are the correct parts. And I know with Hess's law, I just have to add them up in order to get my delta H, which is what I'm actually wanting out of this. I had to do all of this work in order to get it to happen. So I have positive 74.9 plus positive 45.9 plus 135.15, and what I get out of that is 255.9, positive 255.9 kilojoules, which would make this reaction an endothermic reaction because delta H was positive. Okay. Remember, I had to take half of them, so I was able to manipulate the delta H's by taking half of those as well.